Welcome to Chapter 5 of the NFV 101 course. This chapter is about a few selected relevant open source projects. As we discussed earlier, in addition to open standards, open source is playing a major role in NFV and will continue to do so. This shows some open source projects that are popular in various categories. We'll take a quick look at them and then we'll take a deeper dive into a subset of these. At the bottom left, you have NFVI, you have hardware or physical infrastructure, and the virtual software infrastructure above that. So on hardware, there are three open source projects that are popular, and an open source hardware project is sort of an unusual beast. When people think of open source, they normally think of software, but there are successful and vibrant open source hardware projects as well, where designs of servers, storage, networking, and entire data centers is done in the open source. So let's look at the three popular projects. So Open Compute Platform, or OCP, is the far left one, and OCP creates open source specifications and designs for servers, storage, networking, racks, and entire data centers. There's also a telecom working group which has been taking an active role in defining telco-centric hardware specifications, whether it's a rack level solution or virtual OLT. The next one is TIP, or Telecom Infra Project. This project is applying the same principles of OCP. By the way, OCP was started by Facebook and Intel, and a lot of the designs, actually original designs, came from Facebook. TIP has also been started by Facebook and is following in the footsteps of OCP and using some of the same approaches. And TIP's goal is to work on hardware other than sort of standard data center equipment. Could be access equipment, could be radio equipment, and the idea is to come up with commoditized open source designs. Then there is an organization called Open Data Center Committee, ODCC. ODCC is to China what OCP is to the US. For some reason, OCP was not quite meeting the requirements of the Chinese market, so ODCC was formed, and ODCC creates open source hardware very similar to OCP, but with a China focus. So these are some of the major open source physical NFVI projects, hardware-based. By the way, I forgot to mention, OCP also creates white box or bare metal switch specifications. Above that is the virtualization layer, or the software NFVI layer, and some of the popular projects that are Docker for containers, KVM for virtual machines, and I'm not going to go through them at this point because we have detailed slides on that. Ceph is a virtual storage solution. It's a scale-out storage software project. It basically, you keep adding nodes for more capacity, and it's a distributed storage solution. The underlying technology is all object storage, but there are host level plugins to provide a block or a file interface. And as it turns out, Ceph is probably the most popular block storage solution used with OpenStack. OVS is a virtual networking project. OVS is a software-based switch that sits in the hypervisor that provides switching between virtual machines and the external world. It also has encapsulation technology, and through the encapsulation technology, it can do overlay networking as well, where an overlay networking packet is encapsulated in a physical, in an actual packet. Next, you have FIDO. FIDO is also a virtual networking solution similar to OVS, but the technology is quite different. If it gets a lot of flows that need similar processing, it processes them in parallel. So the throughput can be much higher than, for example, OVS. So these are some of the virtual NFVI software solutions. There are others, data plane acceleration technologies that we have not shown, things like DPDK, etc., Open Data Plane, which you could also put in this bucket. VNFs, by and large, are all proprietary. There are some open source ones, for example, Viada for virtual router, but by and large, VNFs continue to be proprietary. On the right-hand side, you see Mano. You see the Vim layer and SDN controllers underneath that. Some of the popular virtualized infrastructure manager solutions are OpenStack and Kubernetes. OpenStack is most popular with virtual machines, and Kubernetes is most popular when the main focus is to orchestrate containers. So it's a container orchestration engine, and we'll look at them in more detail. SDN controllers, the three popular ones are Open Daylight, Tungsten Fabric, and Onos. All of these have slightly different focus from each other, but at the highest level, they're all scale-out SDN controllers where you can do centralized control plane management, with the data plane being in physical or virtual switches and data plane elements. Above that, you have the Mano layer in terms of NFVO and VNF managers. And when I say Mano, it's synonymous to NFVO plus VNFM, even though strictly speaking, the ETSI definition includes the Vim layer. So the two popular Mano projects in the open source are Open Source Mano, or OSM, and OwnApp. We'll look at both of them in a little bit more detail. Open Source Mano also extends the classic definition of Mano by including a design studio, and OwnApp extends the classic definition of Mano by including some SDN controller functionality and service assurance functionality. We'll talk about that in a little bit more detail. So over and above the projects that we just talked about, there are two more. Those two have to do with integration and testing. So taking an entire stack with all these various components and optimizing and testing it for carrier grade requirements. And we'll talk about those projects in a little bit more detail as well. So that's sort of the universe of the most popular NFV related open source projects. And now let's go through a few of them. In the area of NFVI compute, there are two major solutions, KVM and Docker. KVM is a virtual machine technology. It's a hypervisor, and the hypervisor sits in the operating system. So the operating system which it sits on is called the host operating system. It's the one that's installed on this physical server. It takes CPU, memory, NICs, and storage, local storage, and virtualizes it, making each virtual machine feel like it has its own CPU, memory, network adapter, and storage resources. So for that reason, each virtual machine then has its own operating system called the guest operating system, which then runs applications such as VNFs or MEC applications. This is a very mature project. It's over 10-year old. And we already discussed this next point, that it provides a virtual machine that looks like a physical machine to an operating system. There's very good isolation between virtual machines, so isolation and security. And because this is such a mature technology, hypervisors in general, not KVM specifically, but hypervisors, that CPUs have incorporated a lot of this functionality, the isolation and security functionality, which really contributes to sort of good hygiene between virtual machines. An alternative option to NFVI compute is containers, specifically Docker. Unlike machine virtualization, Docker provides operating system virtualization, and therefore it's dependent on the operating system. Because you're not virtualizing a full machine, the container technology tends to be a lot lighter. You can have a lot more density of containers in a physical node. You can have typically up to 10x density, and they also boot faster because, again, you're not booting a full operating system. So they can boot up to 10x faster. But since the operating system is shared, there's less security and less isolation. It also has application management functionality, which we'll talk about more when we go to Kubernetes. And there are different container formats, but Docker is the most popular one, and it's a lightweight method for virtualizing network functions using Docker. So on the right-hand side, you see the picture, physical machine with a host operating system, and using libraries, you virtualize the operating system, creating containers. Now, the same operating system could have a hypervisor as well with a virtual machine, and a container could be run in the virtual machine if you wanted higher degree of isolation. Next, let's go to the virtualized infrastructure manager, and the most popular software there is OpenStack. OpenStack is a project that was started in 2010. So it's a fairly mature project. It's 8 years old. And it's an open source software to manage enterprise and telecom infrastructure. It has an integration engine with APIs to orchestrate bare metal virtual machines and containers. Although I would say the primary strength is virtual machines and more recently bare metal machines. And it has a fairly large global community across 183 countries. The main projects in OpenStack have to do with compute virtualization, storage, networking, identity, and image management. And then there are several others. And through these projects, you can create, as the right-hand side picture shows, you can create bare metal, virtual machine containers, object storage, file storage, block storage. And the main value is that these are all the resource management and creation, orchestration, and lifecycle management is all done through APIs using self-service mechanisms. An alternative to OpenStack is Kubernetes. Kubernetes is a container orchestration engine. It's an open source system for automating deployment, scaling, and management of containerized apps. Where Kubernetes goes beyond OpenStack, for example, it's not a perfect analogy because OpenStack is more suitable for virtual machines and Kubernetes for containers. But using an analogy, Kubernetes goes beyond, and it goes into the realm of application management, which is a point we saw a couple of slides ago. It groups containers into what's called pods, sort of logical units for easy management and discovery, and it handles higher level functions like self-healing, scale out, scale in, etc., simplifying the burden on and reducing the burden on the application itself. It comes out of Google, and it was built using 15 years of experience of running production workloads at Google. So it's fairly sophisticated, easy to use, and fairly mature. So you see on the right-hand side, you have different nodes, Kubernetes nodes, which are running services, and each service is running multiple pods, and each pod in turn is running multiple containers. And then there's a replication controller, which is the master. Now we'll look at two Mano projects. And like I mentioned, when I say Mano, I mean NFVO and VNF Manager, and not the entire stack, including the Vim. So the two popular projects, Mano projects in the open source are OwnApp, Open Network Automation Platform. It's a Linux Foundation project. It's a comprehensive platform for real-time, policy-driven orchestration and automation of physical and virtual network functions. It has a unified design palette. It resulted from a merger of eComp, which was code contributed by AT&T. They actually use eComp in production for their networks. And OpenO, which was a project started by China Mobile, Huawei, and others. The left-hand side shows a very high-level picture of OwnApp. There are two components to it. A design time component on the left to create recipes, services and recipes, network services, VNF onboarding, recipes, etc., policies. And on the right-hand side, you have the runtime, which has two big pieces of functionality. First is service orchestration and lifecycle management. And the second bucket is service assurance. And the way these two work together is once a network service is deployed with VNFs, the service assurance part of the software starts monitoring those VNFs, sends events, alarms, logs, metrics to an analytics engine. The analytics engine sends events to a policy engine, and then the policy engine can trigger actions that go back to service lifecycle management in terms of any action. It could be scale in, scale out, change management, rebuild, restart, whatever the action is. There are three use case demos that the OwnApp community has shown so far, and by no means is this exhaustive. I mean, OwnApp can be used for anything. These are just three that have been used to sort of make the point of what OwnApp is and what it can do. There's a virtual firewall / VDNS use case, virtual CPE, residential, voice over LTE. So these are all actual working use cases you can go look at and see how they're done. The other Mano project in the open source is open source Mano. OSM is under the Etsy umbrella, and it has all the classic NFVO and VNFM functionality that's specified in Etsy specifications, but additionally it also has a design time tool. It was led by Telefonica, British Telecom, Telenor, and its fifth release came out in May of this year, 2018. The philosophy of open source Mano is different than OwnApp. OwnApp tries to be a full stack with full integration top to bottom, while OSM uses an extensible approach with plugins or interoperable pieces. So the plugins allow for different VIMs. In addition to OpenStack, you can talk to Azure, you can talk to AWS, etc. It talks to multiple SDN controllers, and it has plugins to talk to, say, analytics and service assurance software that can then feed into its service orchestrator. So it can do exactly what OwnApp can in terms of real-time closed-loop automation, except that it's through a third-party software as opposed to integrated software. So that's just, neither is good or bad, it's just a different philosophy. Just like OwnApp has three demos, they have three demos as well. 5G/network slicing. The second one has to do with multi-access edge computing, and the third one pertains to enterprise 5G. The left-hand side shows a block diagram. You have the GUI and design time tools. Then you have a network service orchestrator. And underneath the network service orchestrator, you have two pieces: the resource orchestrator, which talks to the Vim layer and SDN controllers via connectors or plugins, and then the network to VNF configuration, N to VC, which has more to do with sort of configuration and lifecycle management of the VNF. And then underneath that, you have the NFVI, Vim, and external SDN controller layer. So that's a quick overview of OwnApp and OSM. OwnApp and OSM are in the same category. So here's sort of a quick list of differences. And we are not trying to do, one is better, one is worse. We are just trying to show some of the key differences, and then as an operator, you can decide which one works the best for you. OwnApp is Linux Foundation hosted. It has 408 contributors. It is a full integrated stack with a very broad scope, including real-time, policy-driven, closed-loop automation. It's had its second release in May of 2018. So compared to OSM, it's 3 releases behind at the same point in time. The footprint is quite large. If you want to just try it out, you still need 32 vCPUs and 128 gigabyte of RAM. OSM is Etsy hosted, 104 contributors. As we already spoke, the scope is narrower with a focus on stability and extensibility. And the extensibility comes in these areas: VNFs, Vim, Mano, and service orchestration. 5th release in May of 2018. And if you want to just try it out, the footprint actually is quite compact. It requires just 2 vCPUs and 8 gigabyte of RAM. Now let's switch gears to integration and testing related projects. So before we dive into the projects, let's talk about why you need these projects. So you have upstream projects. You have OpenStack, you might have OVS, you might have DPDK, you might have OpenDaylight, you might have OwnApp, and you want to integrate all of these to create a full NFV stack. There are 2 gaps. There will be 2 issues you run into. The first gap is integration, security, validation of projects. So upstream projects don't naturally integrate with other third-party open source projects and do interop testing. That's just not part of their charter. So that's a gap, and that's with respect to both integration and security. The second is upstream projects cater to multiple verticals. They work with a horizontal mindset. So OpenStack doesn't say, for example, that I'm only going to work on NFV. They work on many, many use cases. So then you ask the question, then who is representing NFV requirements? Well, that's another gap. So the gap is to provide and contribute carrier-grade requirements and features back to upstream projects. Then you have, so let's say you fill these 2 gaps and you create the stack. Now there's a third gap, which has to do with testing. How do you guarantee the performance, functionality, stress testing, longevity testing, security testing of the entire stack? And that's gap 3. So if you fill gap 1 and 2, you get a NFV reference architecture stack. If you fill gap 3, you get a tuned stack that's tuned and tested for the NFV specific use case. So these are the 3 gaps, and as you might imagine, OPNFV and Cord, the last 2 projects we are going to talk about, do indeed fill these gaps. So OPNFV is under Linux Foundation. It stands for Open Platform for NFV, and Cord actually is also in Linux Foundation. It stands for Central Office Re-architected as Data Center. Their approaches are different. Let's talk about OPNFV first. So the right-hand side of the picture talks about the 3 pillars of OPNFV. The first pillar is integration. That has to do with taking various upstream open source projects that pertain to NFV, aligning them, creating installers that can install all these projects with each other with the right configurations, and then composing these stacks. So that's the job of the integration pillar. Once you have that integrated, you have to test it. And there's a strong emphasis on testing in OPNFV. There's functional testing, there's system testing, performance testing, and more recently stress testing, longevity testing, etc. The third pillar influences upstream projects to cater to NFV requirements. So it might make recommendations or outright contribute code. But whatever code is contributed upstream. There is no downstream fork, for example. Then you see three horizontal bars in the right-hand side picture. And those are efforts that cut across these three pillars: integration, testing, and new features. One is the construction of a CI/CD pipeline. The continuous integration pipeline in OPNFV is quite sophisticated and modern. And if you are looking for a CI pipeline, that's something that should be considered. Documentation and security also cut across. Now, the left-hand side of the picture shows what projects OPNFV integrates. You first have the infrastructure. These are hardware labs spread across the world with a very strict definition of what constitutes an OPNFV pod, which is 6-server configuration. On top of that, it integrates data plane acceleration projects, FIDO, and virtual networking, I should say. So FIDO, OVS, DPDK, and ODP, Open Data Plane Platform. That's another data plane acceleration technology. So it integrates those. And for compute, storage, and network layers, for compute virtualization, it incorporates KVM LXD. For storage virtualization, it's Ceph. For SDN controllers, it integrates Open Daylight, ONOS, Open Contrail, which now is called Tungsten Fabric, and OVN. We didn't talk about OVN, but OVN is overlay networking. So it's a virtual networking only technology that's being worked on by the same people who developed OVS. Above that, you have OpenStack / Kubernetes as the virtualized infrastructure manager project. And at this point, OPNFV integrates one Mano project called OpenBaton, and it is actively looking at incorporating OSM and OwnApp. We didn't talk about OpenBaton, but OpenBaton is also a Mano project that's being developed in the open source. Now, you might ask, how can all these projects be integrated together in one stack? How can you possibly have Open Daylight and ONOS in the same stack? Or how can you have OVS and FIDO, or KVM and LXD for containers? So you're quite right. You can only have one item in each category, because if you put two, then it'll create a conflict. So what you end up getting is a permutation of these technologies into different reference architecture stacks. And in OPNFV, each reference architecture stack is called a scenario. So what you end up getting is a variety of scenarios. So with that overview, let's look at the bullets. Linkage to NFV standard. Some of the people who created NFV, ISG early standards, and OPNFV were the same. It integrates NFV-related open source projects, extensive, comprehensive testing, and develops carrier-grade features in the upstream community, not downstream. The second project that does the same thing is CORD, Central Office Re-architected as a Data Center. In some ways, CORD's focus is narrower, but in other ways, it's broader. The way it's narrower is it focuses only on sort of edge environments. It's not looking at sort of all possible environments. Second, there is no concept of different scenarios like OPNFV. CORD is prescriptive, and it picks the different technologies for each category of functionality. Now, where it's broader is that it also incorporates VNFs. So in that sense, it is able to show end-to-end, optimize end-to-end stacks that have VNFs, orchestration, infrastructure, all in one. So you look at the picture on the left, the hardware is all OCP, Open Compute Platform. So OCP Compute, OCP storage servers, and bare metal switches, white box switches from OCP. Above that, you have Ubuntu and KVM. That constitutes your NFV layer. On the right-hand side, you see the Mano layer. You have OpenStack, which is the Vim. ONOS is the SDN controller. And on top of that, you have XOS, which is the VNF manager, loosely speaking. And this shows the common stack. But then, like I said, you have open source VNFs. Depending on the flavor of open source VNFs, you get different flavor of a stack. So there are three. There's a residential, enterprise, and a mobile cord. So there are three cords. So let's look at some of the bullets on the right-hand side. Cord has helped focus the industry on converging the requirements for edge. It's largely telco-driven. However, many of the requirements are applicable to the cable industry. The stack integrates OCP hardware, OpenStack, ONOS, and XOS. The flavors we talked about already. There's actually a fourth flavor as well, A-Cord. So R-Cord, E-Cord, M-Cord, and A-Cord. A-Cord has an analytics stack, but we haven't shown that here. In conclusion, standards and open source are key to NFV transformation. In previous chapters, we looked at standards. In this chapter, our emphasis was really looking at open source projects. So hopefully you have seen that unlike the PNF world, where everything was proprietary and all proprietary products were procured from vendors, in the NFV world, open source is going to play a big role. And how you procure it is really up to you. You can continue to use the same procurement model and go to a system integrator type, a company that also plays the role of a system integrator and get one-stop shop. You can be your own system integrator and use a disaggregated procurement model where you get support for sort of key open source projects and put everything together yourself. Or you can go even more aggressive and not use any vendors for open source, which is the do-it-yourself model. The do-it-yourself model is not for the faint of the heart. It requires a solid engineering team to be in-house that can contribute code, that can debug issues, that can support internal departments, but it is an option, and some operators have used that approach. CableLabs is involved in both NFV standards, as you saw earlier, and open source projects, which you will see in just a little bit. And the idea is really to represent the interests of the cable industry.